All right, so to kind of continue with our work on linear regressions, let's look at this example. And they tell us S is the sales of frozen food bowls in millions. That's a lot. And the T years since 2000. So those are the two variables. A reasonable model of frozen food bowl sales is S equals 32T plus 312. Now there's a couple things that we want to interpret here. So let's see if we can't do that together. This is kind of like interpreting that equation from our first example in the previous video. So let me switch over to here. This is example G. And I know I'm going out of order here. It's all right. S was equal to, what was it, 31 or 32? 32T plus 312. 32T plus 312. Now let's see what the problem's asking you here. It says, what is the slope and what does it mean in this situation? So let's start with the slope. What's the slope here? For this
32.
particular equation? Yeah, 32, thank you. Slope is 32. And now is the slope increasing? Are sales increasing or decreasing?
Increasing.
Increasing, good. If it was decreasing, what would be different about this equation?
Would be negative.
Yeah,
Minus 3. Oh.
yes, thank you all. It'd be a minus 32, all right? So we've got a couple different possibilities here, and the one that I think seems to fit would be this one down here, because sales are increasing. So the slope is 32, and let me see, should be able to write that maybe. Let's just do that here. 32. The sales of frozen bowls are increasing by 32 million per year. Okay, nice. Now I'll give you a heads up on the next part here, and you'll see one like this, maybe not in the homework, but in the review for your exam next week. The S-intercept is blank. Now, hint or note well that they ask you to type in an ordered pair. But let's just start with what's the S-intercept, or in algebra class it'd be what's the Y-intercept. Any takers?
312.
Yeah, 312, right? That's your Y-intercept, or in this case, an X-intercept, Y-intercept or S-intercept in this case. And the correct answer would be 0 and 312. So what's that saying? That's saying in year 0, which is really 2000, that there was 312 million frozen food bowls sold. Okay. Sales of frozen food bowls in 2005. How are we going to get that for that last part here? How are we going to get the sales for 2005? Well, 2005 is how many years past the year 2000?
5.
5. So essentially what they're telling us in 2005, the value of T equals 5. So we're going to plug T equal 5 into this equation. All right. So let's see. It's going to be S equals 32 times 5 plus 312. So it's going to be 160 plus 312. It's going to be 472 million bowls. Or maybe I should put bowls served, either way. Or a million, food bowls. Yeah, there we go. But are you understanding how we got that? That's what's called our predicted value. That's what this equation says. It might not be exact, but it's probably a good approximation to how many bowls are sold in 2005. Okay.
Really quick.
Yeah,
Sorry.
please.
What
Oh.
would the ordered pair be for that then, for then 2005?
Oh, great question. The ordered pair here would be 5 for the T, and then 472 for the sales. So yeah, it'd be T and then S, which kind of violates some sensibilities for me as an algebra teacher, but for statistics, it's fine. So you've got years after 2000 and then the sales, because the sales depends on the year. So
Okay, thank you.
That's a real good question. Thank you.
So for the other one, for the ordered pair, it's 0, 3, 12. Does that mean T equals 0?
Yeah, so what's going on here, in fact, you can kind of see it here. So if the year is 2000, that means T is 0, because T is the number of years after 2000. So that's where you get T equals 0. And if I put in T equals 0 into this equation, I didn't mean to do that. There you go, never happened. S equals 32 times 0 plus 312. So when I put in the T equals 0, this disappears and I get 312. So kind of following along this format, you put in the T and then the S. I put in a 0 and I get 312. So that's where I got that point from. Thank you, ladies. Those are some good questions. I think those helped out. Does that answer your question, though?
Yeah, thank you.
Okay, wonderful, wonderful. Let's move on to example C. Now, when we start getting into these regression equations, what we're going to be testing is a hypothesis. And I don't have a nice handout for you like I do for some of these things, but our hypothesis is going to be this. Beta 1 equals 0. Now let's think about the model here. Y equals beta 1 x plus beta 0. Keep in mind the author is going to write it the other way. Beta 0 plus beta 1 x. I don't know why. I just, it greatly offends me, but I mean, no, I shouldn't say that. I don't know, that's the way I think it should be, but you know, apparently other people have different ideas. No big deal.
So in the homework, we have to write it the second way?
I think you're going to see it written this way in the homework. If you look back at one of the problems that we did earlier, and of course this would be in the other video, but this one, they wrote it like that, that you have the y-intercept here, and then the slope here. So the correct answer in this one was B, but you're showing the y-intercept first, and then the slope times x. So, yeah, just gotta have to be careful to plug it in that way. I mean, I know, and I relate that if you're used to working in algebra, it feels a little bit backwards. How about this? If beta 1 is equal to 0 is our null hypothesis, what's the alternative hypothesis?
Does not equal 0.
Yeah, it does not equal 0. Perfect. Now, it makes a big difference to know whether or not beta 1 is equal to 0. And let me remind you of what happens when the slope is 0. So when the slope is 0, no, that's not the one I want. This is the one I want. So let's go here and put the slope equal to 0. How come it's not going to 0? Oh, I got this one clicked on. When the slope is 0, all I've got is a horizontal line. And let me adjust the y-intercept a little bit, but it's just a horizontal line. What that means is that knowing the value of x doesn't tell you anything about the value of y. I could say, oh, well, if x is 2, and you say, oh, well, y is 20. I could say, well, what about if x is 4? You say, oh, well, y is 20 again. And then I get pretty tired of this game at x equals 6, y equals 20. I mean, no matter what the value of x is, y is equal to 20. So knowing the value of x doesn't help you at all. It's only when the slope is different than 0 that you actually get good predictive values. So for instance, if I let that be 32 and then change my slope or my y-intercept maybe to 0, I get a pretty good fit of my data. But that's only going to happen when you have a non-zero slope. That's the only time you can use the equation to make predictions. So what if you don't have the equation? What if you can't get rid of this assumption? If you can't get rid of this, if you can't reject H naught, you're going to use y hat, your predicted value, is going to equal the mean value for y. Use this for predictions. And y bar is get the mean value for y. But what if you do reject H naught? Then you're going to use the regression line. You've got a useful regression. And useful regression line, I should say. We're going to use y hat as b1x plus b sub 0 to make predictions. So you got one of these two cases, depending if you reject H naught or not. Now let's follow through with example C. I'm going to do example C 2 different ways. So you're going to kind of get the extended version of example C. But let's do it as it's stated on your handout first. So that would be here. For 50 randomly selected speed dates, attractiveness ratings by males of their female date partners, X are recorded along with the attractiveness ratings of females, or excuse me, by females of their male date partners. Ratings are from 1 to 10. The 50 paired ratings yield this data with a p-value of 0.052. Here's your regression equation. Find the best predicted value of y hat. So that's right here. We want to find the best predicted value for a date in which the attractiveness rating by the male partner was X equals 7. Use a 0.01 significance level. All right, so there's a lot here that we need to unwind, but we can help ourselves by keeping in mind the steps we used to use in chapters 8 and 9. So this is our step 1. We'll state the null and alternative hypothesis. Can someone help me remember what step 2 was? What was step 2 in all our things? Yes?
The significance level?
Awesome. Thank you. Alpha in this case is 0.01. Step 3 is to input the data. That's been done for us, so we're okay there. Step 4. Let's spread the wealth here a little bit. Who else? What's step 4 in all of our hypothesis testing?
Isn't it p-value?
Yeah. And according to the problem, the p-value in this case is 0.052. Awesome, well done. And that brings us to step 5. We're going to compare the p-value to alpha. And the p-value is 0.052 and alpha is 0.01. So the p-value is greater than alpha. What does that say about our regression, or about H0, the null hypothesis?
Fail to reject.
Failed to reject. Thank you. Failed to reject H0. Yay. Now, we came a long way just to find out we don't have to work too hard for this problem. So what the problem asked you was, okay, what's the best predicted value for y hat when x equals 7? That's over here. Well, because we weren't able to reject the null hypothesis, the best predicted value is simply going to be y bar. So the answer to this question is y hat equals the mean, and that mean value was 6. So I've got it circled here in blue. I'll try and hit it a little bit harder here. Right here. That's where they tell you y bar is 6. And that's the best you can do in terms of predicting. It's just say, you know what? I'm just going to use the average because my slope wasn't significantly different than 0. I'll pause here because there's a lot with that one. And if you have some thoughts or concerns or some curiosities, here's a good place to get some help. All right. Well,
can you explain the last part again?
Sure. So when it comes to making a prediction, that is to choose a value for y hat, you've got these two choices. Either if you reject H0, then you could just use the regression equation. But if you don't reject H0, the best you can do is just use this line. Y hat is the mean of your y values. And that's what we chose. We weren't able to reject H0 because our p-value is greater than alpha. So that means you're stuck using the mean for prediction. Doesn't matter what the value of x is. You're just going to use the same prediction for all your variables, all your values of y. It's going to be 6. Now, let's look at that in contrast to a different case. So this is the kind of the extended version of example C. So we'll call this example C bonus, the bonus edition. Here, we're going to change alpha, assume alpha is now 0.10. And let's see how that changes things. So if I let alpha equal 0.010, let's fast forward to step 5. In step 5, we're going to compare the p-value to alpha. And the p-value is 0.052 and alpha is 0.10. p-value is less than alpha. What's that mean? What's my conclusion here?
Reject it.
Yeah, thank you. Reject H naught. Beautiful. So now if I want a predicted value, now I'm going to use the regression equation because I rejected this. So in this case, we get, let's think. Well, the regression equation was given to you in the problem. It was y hat equals negative 0.314x plus 8.04. I think they gave it to you a little differently, but I wrote it my way. Looking back here, they asked us to figure out, well, what's the best predicted value when x equals 7? In this particular case, with that higher value of alpha, you would actually use the linear equation that we came up with. So at x equals 7, it would look like this. Y hat is negative 0.314 times 7 plus 8.04. So put in a 7 for that x. And if you take out your calculator, you'll get 5.842. That would be our predicted value here. So depending if you accept or reject the null hypothesis, you've got two different ways to get the predicted value.
Excuse me, Professor.
Yeah, neat.
Where did the 7 come from again?
Oh, from the problem. So right here, see that purple arrow?
Oh, yep. Thank you.
Yeah, so it said, you know, define the best predicted value of y hat when x is 7. So that's where it came from. All right. Yes, no problem.
Real quick. So what if we failed to rejected it? What would 7 be?
Well, if you fail to reject it, then you're back here where you're just going to use this. And it doesn't matter what the value of x is, because essentially your equation is going to be y hat equals 0 times x plus 6 in this case. So you can put in any value of x you want. You're still going to get y hat equals 6 because you didn't reject this hypothesis. So if that's 0, doesn't really matter what you put in for x, does it? Because 0 times 7, 0 times 700 is still going to be 0 plus 6. So that would be your equation. Does that help out maybe? Kind of plugging in a 0 here for yourself gives you something like this. And then the y-intercept is just the mean of the data. That's what it works out to be.
So the predicted value would be 6 then?
Yeah, the predicted value would be 6, regardless of what x is. That's in the case where the regression is not very useful, that you don't get a good linear fit. But if the regression is useful, then it does make a difference what x is. In fact, if you'd like, Jalal, want to pick another value for x? Just pick something simple.
Like a 9?
All right. At x equal 9, you get y hat equals negative 0.314 times 9 plus 8.04. So let's put that in. Do it on our calculators. Negative 3, how about 0.314 times 9 plus 8.04. I get 5.214. Now that's what x equal 9 here in this case where we're actually using the regression. But back up here, if I failed to reject H naught, what would be my predicted value for y?
It's like whatever they give you.
It'd still be this 6. So it's just always going to be the mean of the y values, which would be 6. So here it's just a nice straight flat line. Here you've got a nice linear equation like that. Still seems to me like you got a little curiosity on that. There's something else I can help out with. Let me know. Does anyone else have maybe something about this that you'd like to get some help on? Because here's a good chance to get it. Okay. Well, you'll see something like this in the homework, so just be aware of it. You know, your predicted value for y is going to depend on whether or not you fail to reject H0, in which case you'll just use the mean, or if you reject H0, in which case you're going to use the regression equation.
So will they give us a mean most of the time?
They'll have to give you one of two things, either the mean or the data. So yeah, they're going to have to give you one of the two. Yep. Okay, so let's look at example D. So again, kind of going back to our handout. So we're going to take a look at some data, plot it, and try and come up with the equation of the regression line. So I'm going to put this data in the chat for you. And there you go. If you would, copy that and let's paste that into StatDisk. I think I already have mine pasted in here. Did that come through okay for you guys? Are you able to paste that in? Should look like what I have in columns 1 and 2. While you're looking at that, let me also direct you to page 490 for the requirements. Yeah, requirements. Now, I didn't give you a handout on this, so my bad. But here's my requirements, or here's the requirements. And I want to focus in on a couple of them. One of the things we saw in the first part of this class was that you really need quantitative data. It doesn't do good in terms of trying to find a regression equation if you have data that's nominal. You can't find a regression equation on what type of roller coaster you were on. So you need quantitative data. And you should also do a visual inspection of the data. See if it looks like there's a straight line pattern that appears. So we'll do that. Now, maybe just relax for a second and you'll let me do that. But I'm hoping that all my chit chat is giving you a time to put in the data. You don't have to follow me on this step because I'll show you a little bit more of a shortcut. But if you just wanted to look at the data, you can click data and then go down to scatter plot. And that's what they're asking you to do, is just do a little quick look at your data. So my data, X values are in column 1, Y values are in column 2, and bam. How does it look? Does it look like this line does a good job representing our data?
No.
Doesn't look great. I mean, it's not awful, but it doesn't look great. So yeah, I agree with you there. But let's actually not leave it to our subjective analysis. Let's take a look at this more critically. And we're going to do most of a hypothesis test here. So your hypothesis in this section are going to be like this, H naught, such that beta 1 equals 0 versus the alternative that it's not equal to 0. This means that you've got a significant regression, that you're going to use the linear regression equation. This says that you're just going to use the mean. So that's our step 1. Step 2, someone new. Here's an easy one. Come on, chime in. What's step 2? In general.
Significance level.
Thank you, Allison. Yeah, the significance level. Alpha is 0.0. Let's go with 5. Step 3, we're going to put it in the stat disk. Put data into stat disk. And then that brings us to step 4. What do I need from step 4?
The p-value.
Ah, well done, Wendy. The p-value. So let me show you how to get the p-value and more. Actually, a lot more. So we're going to go to analysis. And does there look like there's anything underneath this menu that might be helpful? Anything?
Correlation and regression.
Beautiful. Correlation and regression. So the fifth choice down here, correlation and regression, should bring you to this. Our significance level is 0.05, so we're good there. Our data is in column 1 and column 2 for your X variable and your Y variable, respectively. And that's it. Just hit evaluate and you get all kinds of statistics. There's your sample size, your degrees of freedom. Get a lot of stuff here. Correlation coefficient, critical value for R, p-value, etc. But we're interested in the p-value, at least as of the moment, and that p-value is 0.00041. Great. So what's that mean in terms of our regression? Well, that brings us to step 5. Our p-value and alpha. So the p-value is less than alpha. What's that say about a regression?
Reject.
Yes, reject. H naught. So it means we have a significant regression. The equation that represents this has a non-zero slope. That means you can use the value of X to make a decent prediction for Y. So I got to be careful here for myself, but they give you the regression equation and they give it in his form, not mine. So we're gonna have to kind of juggle between the two of us. They give you B sub 0, here's B sub 0, and then B sub 1. But it's not just B sub 1, it's B sub 1 times X. So they're giving you their equation backwards from what I would write it. But that's gonna be your Y hat. Now they wrote a Y. I just guess that they're restricted in terms of the characters they can use, but it's really Y hat. And I'll give you 2 different versions of this. So one of them is the way the author writes it, and the other one is the right way. I mean, my way. I mean, just different. Actually, I got the wrong decimal place here. It's right there. So we'll use some psychic powers to make that disappear. Ready, 1, 2, 3, use the psychic powers. Thank you. All right. So this is what you would use for your regression equation. Are you okay in getting that? Were you able to follow through?
Yes.
Thank you. Thank you. So what I want to do then is I want to make a prediction. I want to predict the value of y if I know the value of x. I'm just going to make one up. So this is just pulling one out of the air. For example, if x equals 5, find y hat. Okay, let's do that. I'm going to use this version of the equation. Y hat is 0.90 times x plus 3.10. And I'm going to plug in my 5 there. 5 times that gives me 4.5 plus 3.1. Sounds like 7.6. So that's my predicted value. Well, what's my actual value? Is there an actual value here? Actual value of y. Was there a value of y in our data set that corresponded to x equal 5? Well, go back to your data set. What's the value of x that corresponds to y equals 5? Or excuse me, what's the value of y that corresponds to x equal 5?
$6.54.
Thanks, Jalal. 6.54. Nice. So how did our value do? I mean, this was the predicted value. This was the actual value. Did we do really good? There's a little bit of an error, or sometimes it's called the residual. The residual is defined like this. It's going to be y minus y hat. Your actual minus the predicted. And in our case, it's going to be 6.54 minus 7.6, which gives me negative 1.06. Not bad, not great. I mean, it was okay. But we probably didn't really expect a great fit here. I think somebody at the beginning that says, well, it's not really that good of a fit. Do you remember how we can judge qualitatively how good of a fit we got? What was that fancy statistic that we talked about in the first video that told us how good our line did? Maybe we can look back at the output and remind ourselves.
R squared.
Ah, R squared, excellent. So let me go back to this, and I'll probably have to rerun my regression. That's okay. Just take a second. 1 and 2. The value of R squared, let's see right here. Coefficient of determination, R squared, is 0.767. So that's actually not too bad. R squared equals 0.767. Now let me show you kind of a little trick here. Well, a couple things. First of all is the scatter plot. So the scatter plot shows you what we saw earlier, but then there's the residual plot. Basically, it's plotting all these values, the residuals, the predicted value minus the exact value. And wow, you get something like this. This is not what you want to see. There's a pattern to this data. And that pattern kind of suggests that, you know what, you could probably do better with a different model that accounts for more. In this case, there's a quadratic shape. The good news for you is that we don't have to deal with this in this class. We're just going to stop and say, you know what, all we're concerned about is a linear model. In fact, if I know what R squared is, I should be able to find out what R is. So let me go to my calculator here, and I'll clear out a bunch of stuff. R squared was 0.76745. That was R squared. But if I want R, I can take the square root of that. So let me take the square root of that. And oh, I get 0.876. So the square root of R squared gives me R, which is my linear correlation coefficient. And that tells me how much of a straight line this data represents. Is it a perfect straight line? No. What would the value of R be if it was a perfect straight line? Does anyone remember what would the value of R be if it was a perfect straight line?
Would it be 1?
Yeah, thank you, Aubrey. It'd be a perfect 1. All right, so we're somewhat close to that. Was it perfect? No. And you can see that here. We're off. In fact, the fact that we're off in kind of a pattern here really suggests that there's more you can do. Now, this is beyond what we're going to have to work on, but you could actually find an equation. What's missing there is what's called a quadratic term to make it like a parabola. So let me just play around here and plot the data real quick. So there's our data. If in addition to the linear term, that is something times x plus a constant, if I had a squared term, that would probably do pretty good in fitting this data. Let's turn it on, see what our regression equation looks like. You think we got a good fit there? What do you think? Is our model fit pretty good? Yeah. In fact, you can see that the coefficient of determination, R squared, is a perfect 1. You're not really going to get much better than that. You can't get much better than that. That's the highest you can get. All right, you don't have to worry about those quadratic terms. We're just going to worry about the linear terms and finding a linear model. So, all right, I think we're done with example D here. There was a little bit more output that maybe I'll talk about from StatDisk. So let me go back here. Results. So we looked at your coefficient of determination. That was R squared. We've got our slope and our intercept out of this. If you're curious, if you took this value of total variation, divided it into the explained variation, the ratio of these two, explained divided by total variation, should give you your R squared. Should give you exactly that. Now, if they ask you for a test statistic for this stuff, it's like, well, what's the value of your test statistic They're probably talking about, let me see, a formula on page 490. And let's see, do I have my text open? No, I don't. Sorry. Now the formula is not something that I'm going to quiz you on, but in case you get stuck being asked for it, then this is what they're looking for. And it'd be nice if it let me turn to 490. 490. No, that's not the right page. Sorry. Question 479. My bad. 479. Down at the bottom, they give you means to calculate a test statistic, and it's right here. This t value. And they show you an example of how to do that one. It's not something that I'm going to require. You might run into it in one of the homework assignments, though. I just can't weed out every little thing here when the computer's assigning it. Sorry. All right, last problem. And we're going to jump up to F. So I want to show you something about F. Now, when you get to F in your homework, you're going to have to input the data. So if you click the magnifying glass over here to the right, it'll zoom in on this box, and then you're going to need to come up with the X and Y coordinates. So like the bottom one in this hash would be have coordinates of 5 and 3, and then 5 and 4, 5 and 5, etc. So let me put those in your data set for you, or in the chat for you, and you can copy them there. I would suggest that you use this lone one out of the way here. Put that in last in your data set, because for part B of this